we're ready to go. My name is Lawrence Kincheloe. I'm an artist from Factory Obscura, as well as I also volunteer for open source hardware, so I'm wearing a lot of hats today. Thank you for Techlahoma for doing all the work they do. They provide the space, they provide snacks, they provide a wonderful venue for what we do. So if you get a chance, go look at the website, techlahoma.org, and see what you can do to kind of help. For some of you that don't know, Factory Obscura is an artist collective started in, I want to say 2016, maybe 2017. They've done three to four productions so far, one called Shift, Beyond, and the one that's upcoming is called Mixtapes at the Womb. Shift and Beyond have both closed. Beyond closed in beginning of January, so it's been a couple of weeks since that closed. So what we're talking about today is some of the tech behind some of the art that we did. I worked on the tech team. What I did is I actually collaborated with artists, and what we did is artists would help kind of like come up with an idea, and the tech team would kind of help implement it. So it was a really good synergy between art, tech, and science. And so it's been a lot of fun, and I really enjoyed the experience. But this is mostly about some of the trials and tribulations and the creativity that came out of this. So we're going to talk about primarily I got three different examples tonight. One is the star panel, which is this guy right here. We've got a neuron, which is the blinky thing over here. And we've got a sound panel, which is this guy right here. And I'll get to each, and I have some more that I can talk about, but I didn't have physical examples of those, but these are good representation of what we did. So the neat thing about Factory Obscura is that we do a lot of community building and volunteer. On the picture on the left is a volunteer night where we're building the Beyond experience. You can actually see people in the background all working on various pieces of it. And in the foreground, you can see the backside of the star panel. The star panel is made out of, is a combination of individually addressable NeoPixel style LEDs, along with PMMA fiber acrylic that's been glued together. The process we used was, it was kind of like this weird mix of like what do we have on hand versus what do we need to get. So we had some donated foam panels, and we used the foam panels to secure the fiber. And then we used some geotech plastic meshing, which is normally used for architectural landscaping, to secure the panels to a big sheet. If I had different materials, I would have done it differently, but for the most part, it worked out pretty well. The neat thing we did is you can see in the giant spider forest in the background. What we did is we actually used a spray adhesive, like I think Super 77 or Super 76, like 3M spray adhesive, to spray the tips of the fibers, and when you pull them through, it actually locks the fibers into the foam. And so that's how most of the fibers stayed in the foam without falling out. And we discovered that I got really persnickety about keeping all of the fibers, like the ends, perfectly sheared off until I realized that didn't really matter that much. And then it became a lot easier because we just used the X-Acto knife to just cut, slice, and then put things together. But the first maybe 100 were perfectly sheared and aligned, and I got a great color throughput, but it turned out it didn't really matter. I learned a lot in the process. The other thing that we used a lot of is hot glue and super glue. You can actually see in the bottom of the left-hand picture a little super glue bottle. I went through about 10 types of glue and everything I could think of to get these things to stick. But it turned out that a gel-based super glue was the best option. And what it did is it allowed you to stick. What we did is we made a 32 fiber bundle of LEDs. We sheared them off so that they're perfectly flat. sanded them down so they had a rough surface. And then they used the super glue to stick them directly to the NeoPixel style LED. And that actually did a really good job of like creating a bundle. You can kind of see, I got an example of it, so we can see the back of it after the presentation. But you can kind of see the beginnings of the bundles. But I cannot tell you how many times I thought I had the perfect bundle material, and then like it would come immediately apart after like giving it a little bit of a tug. The other thing that this thing was built out of was hot glue. You'd be surprised how many art projects are basically built out of like nothing but hot glue and good intentions. And this project's no exception. We used it for everything from holding down, using it as like vacuum material to keep the foam from pulling out of metal twist ties that we use to secure the foam to the geotech. We used it for as a temporary holder to hold the fiber in place while we were gluing everything together. We used it for as backing material, and we basically, in some of the other examples of other projects we did, we basically like glued the crap out of everything, as the glue everywhere. Here's an example of one of the panels on the wall. And here's a quick build down of what actually went into it. So individually addressable LED strips, acrylic, plastic, fiber optics, gel, super glue, foam blocks which actually held the fiber in place, lots of hot glue. The aluminum tape was interesting. That actually helped kind of block and direct the light at the very tip, because what happens is that the individually addressable LEDs will, most of the light gets captured by the fiber, but some of it still escapes because of the angle of projection of the LED. Usually the LED's got about a 120-degree projection radius. So what the aluminum tape does is it helps kind of like act as a light block, but also acts as a reflector to reflect that light back into the fiber. So it makes it a little bit brighter. These are all 12-volt DC power supply controlled, and we use a LED controller. At one point, I had visions of doing a fancy, Raspberry Pi enabled Starscape that was going to be like controlled by the Raspberry Pi and the touch panels and everything else. But what it turned out is that using the off-the-shelf LED controller was good enough, and quite frankly, in a lot of these projects, good enough is where you need to be. So next time. Moving on to the sound panels. I don't have as many good pictures of the sound panels being produced. I had one of just like a laptop and like tools scattered everywhere, but it's like, it doesn't really tell you what went into it. Because every time somebody looks at the sound panels, they're like, that's so cool. What went into it? It's like lots of coding. I can show you lots of coding, but it doesn't look as impressive as everything else. But the project is really neat. I think some people were playing around with them earlier, but if you hadn't seen it, what they are is that they are a Raspberry Pi running pure data and a custom Python script that converts the Adafruit capacitive touch hat into pure data input, and it uses a USB sound card and audio amplifier to produce sound. And so it uses the bare conductive style conductive paint and in conjunction with acrylic spray to kind of keep the bare conductive paint from getting everywhere, and the capacitive touch hat as the user input interface. So what it does is that when you touch one of the black panels or one of the black symbols, it sends a signal to the capacitive touch hat, which then gets converted into a Python, which then converts it into pure data. And the pure data actually is it's kind of like a sound synthesizer builder. It allows you to create sound effects, and it also does a whole bunch of other things, but primarily it's for art, visual displays, and sound displays. I worked with an artist named David Weber, who was the sound engineer and sound designer, who basically had the idea for the pictographs on the actual display, as well as the pure data synthesizer portion. So a lot of this was as a brainchild, and my major contribution was basically getting to work on the Pi, the capacitive touch interface, the bare conductive paint, and the clear acrylic spray overcoat. And I think it was a lot of fun working with an artist to kind of like take their general idea of what they want to do and then make it really special with some like physical computing interface stuff. So and the way it works is that can you see me? Okay. The way it works is that this one in particular uses a series of touch This one uses an adaptive screen, so when you push one of these, it doesn't sound like it does anything. It changes the sound. So you can like, or if you have two hands, you can actually do it all at the same time. So, and that's kind of that. When we hit the lights, we'll flip it around. We'll kind of see how it works on the backside. And this is some of the LEDs and light switches we did. We've got the neuron in the corner there, and some of these pictures are pictures from Shift. Shift was less, I guess, technical, but still very interactive experience. We used like the LED flowers on the top right screen. Those used a combination of like UV LEDs and UV and blue LEDs to kind of get some shapes and colors that you can't really reproduce with an RGB LED. And they also use like translucent petals to make it work. The neurons in the back, you can kind of see, I've got one example right here. They look a lot better when they're actually being displayed, and I got at least one video of it. So I think these are going to play. So you can see here, like they're basically all blinking kind of in tandem. I've got one of the white ones here, and I don't think I've got a good video of it. Yeah. So the way these worked is that they've got a capacitive, not a capacitive. They got a momentary switch in there. That's a contact switch. What happens is that you can see how they kind of blink randomly. When you hit it, the contact switch cuts the power for all the LEDs, and the blinking becomes in sync. So it goes from kind of being like a gentle pulsing sound or pulsing light to an abrasive blink, 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 blink. And then they've got an individual RC circuit in each LED, and then they'll slowly desynchronize and become kind of a gentle twinkle again. So in this case, each one of those, let's do this. Each one of those neurons was on a metal spring, and so when you hit one of them, everyone along the pathway would basically reset. So you could literally like strike a thought by smacking one of these, and they would all like reset, and they'll all blink together in unison until they would all settle down back into their random state. And the other piece we did was a star display. This one used a series of switches you can see in the bottom corner, and each one of those, when you turn them all off, all the stars would turn off, and when you hit one at a time, they would all, like one of the star patterns would show up, and these were all constellations. I don't have a good picture of it, but we had like a snake, we had a crab, we had a dragon, we had a couple of other constellations. Really simple to do. It was just basically some LEDs all bundled together with some switches, but working with artists basically made what was essentially just a bunch of LEDs into a really interesting project. So we can hit the light switches. We will. You can kind of see here. You can see the it looks a lot better in the dark. We can see the light panel here, how the LEDs all kind of like twinkle gently. And you can see here, this guy is gently twinkling, but when you give it a tap, it all blinks together, and they'll slowly begin to desynchronize, and then it'll kind of start gently twinkling again and stop blinking. There it goes. So really simple stuff, but it's kind of, I think it's not the individual components, but it's the aggregation of the components that really kind of bring us together. Also, the white plastic here, this is this is called a friendly plastic. It's a low temperature plastic. You can actually mold it with your hands. And so I worked with an artist, I'm going to forget his last name, but he basically did all the sculptural elements. Can we hit the lights again? Thank you. All right. So at this point, I'm going to flip everything around and kind of open it up for questions.
And as your star field, some of them are brighter than others. Is it just the direction you're looking at them from, or are some of them actually?
So the question was, why are some of the stars brighter than others? It's purely happenstance, and it's also the quality of the cut and also the angle at which they're inserted. So like the brighter they are, the better the cut on the surfaces, and the more aligned they are on the LED themselves. The weird thing about an RGB LED is that they've got actually 3 LED elements inside of one single chip package. And so even though I've got a bundle about or half a centimeter in diameter sitting on top of that LED, and so that even though that LED gets evenly illuminated, certain fibers in that fiber bundle will be sitting right on top of that LED. So it's a combination of quality of the surface finish, its placement on top of the LED, and also its location out on the field. So
Makes a good effect.
When people were putting together, they were asking like, so how do I put these? You want me to put them in one location? I was like, no, just scatter them across. And so we have each LED is kind of like scattered across different parts, so it kind of like blends together. And we picked a pattern that blended well. So. Okay.
So did you just push the fibers through the foam?
Yes. So the way it worked is that the fibers, you just push the fibers through the foam, and they'll mostly stick in place. But to get them to stick, the question was, how do the fibers actually stick in the foam? The spray adhesive, it'll stay tacky for a couple of seconds. So what you do is you spray it, and then you pull it. And then when you pull it, it allows it to, when the adhesive sets, it sets inside the foam. And that allows it to actually be fairly stiff. So you can give it a tug, and they're pretty robust. They do come out, but they're pretty easy to repair, and for the most part, it's been, I mean, this could have gone horribly. And quite frankly, I'm glad it survived as well as it did. So.
But you didn't have to prepare the foam to put the fibers through?
No, the foam was, I mean, I think it's just a urethane foam. So there's not much I had to do to the foam directly. I didn't have to there's not much I could have done to the foam anyways.
Are they set up in any specific constellations or just sort of random stars?
So the nice thing about doing a star pattern, especially one where where you're trying to actually emulate nature, is that stars are fairly random, and people are very bad at doing random things. So by telling people to just stick them wherever they want, we actually got a significant amount of variation and consistency and patterns, even in what started off as just kind of like a evenly spread them across patterning. So there's no intentional pattern, but there's a pattern nonetheless.